Greetings and thank you for joining me in this video from chapter 3 for normal distribution for A-level maths. So we've seen obviously the binomial distribution, which deals with discrete data sets. The normal distribution is an incredibly important distribution for continuous data which models various real-life phenomena, which we'll see. So this is quite a big chapter. It does get quite a bit trickier towards the end, but these first couple of chapters will ease you in quite nicely. These first sub-chapters, I mean to say, will ease you in nicely to understanding what's going on. So because this is statistics, I would like you to recap on some Year 12 stats, just to make sure you're in the right frame of mind to get going with this Year 13 stuff. So here's 3 warm-up questions for you to try. The third one's a histogram. So try these now, press pause and try these ones on your own. Then press play to see what the solutions are, and hopefully you'll see that yours are correct, as are mine. So let's have a look then together at warm-up question 1. So question 1, in an experiment a fair coin is thrown 20 times and the result recorded. Give 2 reasons why this experiment can be modelled using the binomial distribution. Well, there's actually 4 possible things you could say here. You just need to say any 2 valid reasons from these 4. So the first thing we could say is that there's a fixed number, unknown number of trials. In other words, there's 20 throws, there's 20 trials. There's a fixed number of trials, that's when the binomial can be used. The second one, maybe even more importantly, is it's binomial if there's only 2 possible outcomes. So if we're throwing a coin, those outcomes are going to be heads or tails. Bi means 2, only 2 possible outcomes means we could consider it to be binomial. The third thing we could say would be that each throw can be assumed to be independent of the others. So each time you throw a coin, the probability of a head or tail on each throw isn't affected by if it's been a heads or tails before. And the last thing we could say for this one is that the probabilities remain constant from one trial to the next. So it's going to be 50-50 throughout if it is indeed a fair coin. So that's A done. So this is A. Now we can think about B. So for B, we need to calculate the probability that 8 or fewer heads are recorded. So for B, we're having to work out the probability that the observed number of heads is 8 or fewer. Now, here what we need to say is that X follows a binomial distribution, 20 trials, and the probability of getting a heads on the coin, if it's a fair coin, will be 0.5. So I'll just remind you how you can do this on the class whiz. So first of all, I'd suggest switching the calculator on, of course. Then we press menu, scroll to option 7, distribution, go for binomial CD, which is this one, press option 1, and press variable. We want to work out the probability of getting 8 or fewer. So cumulatively, that's 8 out of 20, probability of 1 successful heads being 0.5, press equals, then equals again. We see this is approximately 0.252. So about a 25% chance of only getting 8 or fewer heads. So you're more likely to get 9, 10 or more. 8 or fewer is relatively few heads, that's why you're more likely to get 9, 10, 11 or whatever. Let's now have a look at warm-up question 2. So here's warm-up question 2, and this question I've included just as an excuse really for you to relearn how to use your calculator. Calculate the mean given by the letter mu and standard deviation given by this letter here, which is sigma. So what we need to do on the calculator, of course, you could do this manually using the formulas, but it's much easier with a calculator if possible. So we're going to press menu, then we go to option 6, statistics. We've only got one variable, so press 1 for one variable calculations. Then we just input these data values. So 2, 3 times, so 2, 2, 2. Then got 1, 3, so press 3 once. Then 1, 4. We've got 5 3 times, so press once, twice, thrice for 3 5s. Then a 6, and finally a 7. When you put all the data in, we just simply press OPTN for options, then press option 3 for one variable calculations. So press option 3, and here's what we need. So mu, mean, is given by x bar. So the mean is 4.1. So we just write this one down. Mean is 4.1, and the standard deviation you can also get from the calculator. So standard deviation is this symbol here, sigma x. Standard deviation is 1.7 for this data set. And that's all there is to it. So just make sure you remember how to use your calculator as a point of question 2. Finally, question 3 is this histogram. So it's a partially completed table and a partially completed histogram giving ages of passengers on an airline. There were no passengers aged 90 or over, it says. So this is going to be very important for part C. There were no passengers aged 90 or over. First of all, we need to complete the histogram. For a histogram, we need to remember how frequency density relates to frequency and class width. And it relates like this. Frequency density is frequency divided by class width. So what can we work out first? Well, we know this bar from 5 to 20 is here. That's got a frequency of 45. So for this one, we can work out the frequency density. So frequency density for this one is a frequency which is 45 divided by the class width. From 5 to 20, that's a width of 15. So 45 divided by 15, that gives us 3. And frequency density essentially is the height of each bar. So if that's 3, then we can see that each big square must be worth 1 unit of frequency density. So 3, 2, 1, 0. We've therefore worked out our scale now. So going up, that must be 4, this must be 5, and this top bar must be worth 6. So now we know that, we can work out the other bars as well. So this one here will have a frequency density of 5 divided by 5, which is 1. So this bar is going to be 1 high, so we can fill this in very easily by just doing 1 across here, like so. And this bar here, from 40 to 65, that's a width of 25, and we can see here it's got a height of 5.2. So for this one, we can work out frequency. So frequency is frequency density, which you can see as 5.2, multiplied by the class width. From 40 to 65 there's a width of 25. So if we calculate 5.2 times 25, that will tell us the frequency for that bar. So 5.2 multiplied by 25, that gives us 130. So there's 130. Now, I have missed off this bar from 20 to 40 as well. So for 20 to 40, I can work out the frequency density by taking the frequency, which is 90, and dividing by this class width. From 20 to 40 is a width of 20. So what's 90 divided by 20? You could work that out without a calculator, but if you want to use a calculator, that's absolutely fine. 90 divided by 20 will give you 4.5. So this one, we need to do a bar which is 4.5 high, which will go here. Like so. So what I could do, I could actually just fill in this bar here. I'll do the other one as well. Do you need to shade it in your test? You know, probably not. As long as you make it very clear where the bar is vertically, should be absolutely fine. So that's that one done. And then the first one was here, so I'll just colour this in as well. Finally, I need to fill in this frequency as well. So frequency is this frequency density, which the height from 65 to 80 is 4, as you can see, and this class width is 15. So 4 times 15, this will give us a frequency of 60. So now we've filled in the histogram and we've completed the table. Part B, we have to use linear interpolation to use that to estimate the median age. So what we can do first of all is find the total frequency. So what's the sum of all these frequencies? Well, let's work that out now. So we've got 5 first. Just move this calculator to the side. So we have 5 plus 45 plus 90 plus 130 plus 60 plus finally this one in the corner. 331. So the sum of all frequencies is 331. So therefore the median Q2 will be this value divided by 2, and we can just simply divide it by 2 because age is a continuous variable. We don't need to add 1 then divide by 2. If you did that, the mark scheme would allow it, but you can just simply divide this by 2 to work out the medianth value. So 331 divided by 2 is the 165.5th value. So whereabouts is this 165.5th value? Well, what we can do here is a cumulative frequency, a running total as we go along. So up to that point is 0, plus 5 is 5, 5 plus 45 is 50, 50 plus 90 is 140, 140 plus 130 is 270, 270 plus 60 is 330, and the last one, 331. So 165.5 must therefore be in this interval. So it's after 140th, but before the 270th. So how far after 140 is 165.5? Well, if we do that, just subtract 140, it's about the 25th one in this interval. There's 130 people in this interval, so it's about the 25.5th person, if that even makes sense. So this interval starts at 40, so therefore we say the median, we start where this interval starts, so start at 40, and then like we said, it's about the 25th person in, so then do that fraction out of the total number of items in this interval, which is 130. So it starts at 40 plus it's this fraction in out of a full width of 25. So it's going to be this fraction through this interval. So then if we calculate this, we'll get what we need. So it's 40 plus 25.5 out of 130 times 25, and that gives us approximately 44.9. So the median age is about 44.9 years. Lastly, part C, we're told what an outlier is defined as being anything greater than the upper quartile plus 1.5 times the interquartile range. So we're told Q1 is 27.3 and Q3 is 58.9. We now need to determine, giving a valid reason, whether or not the oldest passenger could be considered an outlier. Well, what we can do from this one, using these two figures here, we can work out the interquartile range by doing one subtract the other. So from this, the interquartile range, I'm just going to call it IQR, will be 58.9 minus 27.3. So let's just calculate this now. 58.9 subtract 27.3. For that we get 31.6. So therefore 1.5 multiplied by the interquartile range That's going to give us, let's see, 47.4. Okay, so 1.5 lots of interquartile range is 47.4. So this bit here is 47.4. So we can now work out what Q3 plus this is. So Q3 plus 1.5 times the interquartile range. We'll just move this up. I seem to always run out of space. I apologise if you've spotted this about my writing before. I never seem to learn. Q3 plus 1.5 times the interquartile range. Well, Q3 is 58.9. Then plus 1.5 times interquartile range, we worked out was 47.4. What does that give us? I'll add on 58.9. We've got 106.3. So an outlier would be anything greater than 106.3 years old. However, the question clearly says there were no passengers aged 90 or over. So therefore, no one is going to be this old, because that's older than the oldest passenger. The oldest passenger isn't more than 90 years old. Therefore, not even the oldest can be considered an outlier. So therefore, no outliers. If you want to explain fully, it's because 106.3 is older than the oldest passenger. And that's really all we need to say. So that's question 3 done, and therefore the whole lot of the warm-up exercises. So let's have a look now and think about what we mean by the normal distribution. So first of all, discrete and continuous probability distributions. So let's start with what we know. A discrete random variable, like you've seen in year 12, allows probabilities to be calculated for any number of individual events, whereas a continuous random variable provides probabilities within a specified range of events. Moreover, the probability that a specific event occurs using a continuous random variable is 0. So looking at question 1 of the warm-up as an example, let's see what we're going to have. So question 1 from the warm-up, we were throwing a coin, heads or tails. So that's a discrete distribution because heads and tails are countable, and you throw the coin either once, twice, 3 times. It's discrete, it's countable. So here would be a standard distribution of the number of heads expected from 20 throws. So you'd expect on average about 10 out of 20 heads, in other words literally half the time you'd expect it to be heads. Then the fewer heads you get, the rarer it is. So for example, it's very rare you only get 3 heads, and it's equally rare you get 17 heads. And although technically you can get 0 heads, that is so unlikely that bar is unreadable. So this is for a discrete distribution, in our particular case, throwing heads on a coin. It's binomial as well, like we said in warm-up question 1. So if we call this distribution big X, it models the number of heads from 20 throws on a fair coin. And there's a symmetry as well about this curve. So note the symmetry about the peak x equals 10. Each bar going away from 10 is of equal height in ascending order. That's because in theory, the mean number of observed heads over multiple sets of 20 throws should always be 10. 10 would also be the expected modal number of heads. You'd expect to get 10 heads more than any other number of heads recorded if you did multiple experiments, multiple lots of 20 throws. In this case, the probability that big X takes on any particular value little x corresponds to the area of each of these bars above x being 1, 2, 3, and so on all the way up to between 20. So for example, this bar here is approximately double this height 7, let's just say that the probability of getting 10 heads is about double, maybe slightly more than double, than the probability of obtaining 7 heads, for example. So a discrete probability distribution obviously is given by a discrete random variable. What now though if we talk about continuous distributions? Well, figure 2 here, that's a continuous distribution given by a curve. Now this curve is called a normal curve. This is often called a bell curve, which is going to be the focus of this entire chapter. So if we imagine another distribution, but this time, rather than being flips of a coin, imagine it's weights of adult specimens of a particular breed of dog, in kilograms say. Imagine 2 this time, but the mean weight of the adult dogs is 10 kilograms, hence the peak here above 10. So we could model this using a continuous random variable y, such as this probability distribution curve shown below. So it's continuous because weights is a continuous variable, as would be lengths, as would be masses, as would be heights or lengths. So here the probability of observing a dog weighing exactly, for example, 9 kilograms is 0, since weight is continuous. That might seem a strange idea, but let's imagine you think a dog is 9 kilograms. If you use accurate enough weighing scales, you'd find the weight might be 9.1, 9.01, maybe 9 kilograms plus 1 extra atom's worth of weight. But you can't actually ever get exactly 9 kilograms because the idea of having an exact weight is just imaginary. Because if you imagine it accurately enough, it will always be slightly above or slightly below 9 kilograms. You can't actually measure to within a molecule or proton's accuracy. So for all intents and purposes, getting an exact weight of 9 kilograms is, in practice, 0 chance. So what we could do though is think about probabilities of observing weights up to 9 kilograms or at least 9 kilograms. We can consider instead a range of weights rather than a precise weight. And we can calculate that directly from the area under the curve within chosen limits. For example, the weight being up to 9 or the weight being greater than 9. So rather than calculating the area of a discrete certain bar, like with the coin throws, here we'd calculate the area under the curve between a range of values for this axis along the bottom. Consequently, the total area under the curve of a continuous probability distribution is equal to 1, because the sum of all probabilities, as you know, has to equal 1 in probability. So, the normal distribution next. So the continuous variables generally encountered in real life are more likely to take values grouped around a central value than to take extreme values. The normal distribution, sometimes called the Gaussian distribution, named after Carl Gauss, who formulated it, sometimes called a bell curve because it looks like a bell shape. This is a continuous probability distribution that can be used to model many naturally occurring characteristics that behave this way. So examples of continuous variables that can be modelled using the normal distribution are as follows. So heights of people within a given population, birth weights of babies would be another one. IQ is a common one, you'll see this on social media. 1% of people can solve this, you must be a genius to solve it, click here. IQ is a main one, as is, for example, errors in scientific measurements. So all these here and others would have to be continuous. Size variations in manufactured objects is also another one. So what does this normal distribution look like? Let's have a look at its properties. So these histograms show the distribution of heights of adult males in a given population. So as the class width reduces, let's have a look how distribution gets smoother. So you'll see how this becomes a normal distribution. You'll see there's a symmetry about the biggest bar, and it goes down either side, but it's not quite symmetrical yet, but you can see there's a vague looking of symmetry here. So these have a width of 10. If we make this width narrower next, consider widths of 5 centimeters, it would look more like a bell shape. It would become smoother and look more like a curve. If we did it again and took more people and more data and found the heights of thousands of adults, thousands of males, it become more and more like a bell curve. And if we did this again and again and reduced these widths smaller and smaller each time, we would actually see that it slowly become a smooth curve. It becomes bell-shaped and would end up being symmetrical about the mean height. So the curve would be this one in black, it would tend towards, and the mean, mu, would be in the middle, then symmetry either side of that. The standard deviation describes the spread of the data. So in this case, the standard deviation would relate to the heights of the males. The bigger the standard deviation, the wider this bell would be. The smaller the standard deviation, the narrower the bell would be. So let's have a look at this. So this graphic here is 3 different normal distributions with 3 different standard deviations. So the size and shape of a normal distribution is determined by the mean and the standard deviation. These are the 2 main parameters that define the normal curve. So like I'm saying, these 3 normal curves in figure 3 here have the same mean. As you can see, the peaks will always relate to the mean. So we've got the same peaks each one. So the mean mu is the same for each, but we've got different spreads about the mean. So as you can see here, C, the blue one, has a short curve, but it's very widely spread. It's very broad. So C's got the biggest standard deviation. B's got a standard deviation which is smaller than C, but not as small as A. And A is the tallest and narrowest curve. That shows you that A has the smallest standard deviation. More items here for A are closer to the mean. So there's less spread from the mean in A than there is for the other curves B and C. What if you had it where the standard deviation was the same but the means were different? Well, you'd have something that looks like this. If the standard deviations were the same, then what we'd have would be the curves being the same width. But here, the means would be different. For example, for this one here, the mean for the green is down there, the mean for the red is here, and the mean for the last one is over here. So different means, but the same standard deviations for these 3. If x is normally distributed, we write x follows a normal distribution with mean, mu, and standard deviation squared. So the second number here is actually the variance. The variance is the square of the standard deviation. So for example, if this number here were 9, that would mean the standard deviation would be 3. So if it isn't given in this number here, where it's a number squared, you need to square root the number to find the standard deviation. The second value is actually given as the variance. So there's what the normal distribution looks like. So the mean mu is the peak of the curve, and actually we've got the same proportion of the area under the curve as we go standard deviations away from the mean. So let's talk about this next. Properties of it. It's symmetrical about the mean. For the normal distribution, the mean, median and mode are all the same. It's a bell-shaped curve with asymptotes. The asymptote is here. It approaches the axis at this side, but never quite touches, even though it looks like it does, and approaches asymptotically here, but never actually quite touches. It gets so close, effectively, you can think it almost may as well touch, but technically it never actually quite touches. It approaches here asymptotically. It's got a total area under the curve of equal to 1, because it's representing a probability distribution. The sum of all probabilities has to equal 1. And it's got points of inflection at the mean plus 1 standard deviation to the right, and also the mean take away 1 standard deviation. So these are points of inflections where it changes from curving downwards to curving upwards. It's where the curvature changes from convex to concave, or from concave to convex. It does have a formula as well. which is this, and do not panic, you don't need to know that function, you don't need to remember that. That is from the mind of Carl Gauss. That's not the easiest function you will ever see in your life, and luckily you don't need to memorize that or need to actually do much with it at all. But if you need to know or wanted to know, there it is. Now, like I was saying about the proportion of the curve, on the mean, plus or minus one standard deviation from the mean, that will always account for a normal distribution of about 68% of all the data. So 68% of all the data lies within one standard deviation from the mean. If you go plus or minus 2 standard deviations from the mean, that's going to be more of a curve. And it turns out plus or minus 2 standard deviations away is 95% of the data, approximately. It's not exactly 95%, but it's very close, always to 95%. Then if you go to plus or minus 3 standard deviations away, as you can see, that's almost the entire curve. Plus or minus 3 standard deviations away, which I'm going to show you in blue, that's 99.7% of all the data. You can see here maybe there's a tiny bit of a curve that isn't included in that, but that's 0.3%, 0.15% either side. So plus or minus 3 standard deviations, you've pretty much got everything. You've got all the data points, more or less. And although a normal distribution can take any value, in practice, observations more than 5 standard deviations away are so close to 0 that for all intents and purposes, we can assume they're as good as 0 actually. So that's the key definitions and properties of the normal distribution. Now it's a case of having a look at some problems and calculating probabilities using this normal distribution. So, worked example 1. Weights W kilograms of a population of Bengal tigers are normally distributed with a mean of 220 and standard deviation of 8 kilograms. Sketch and label the distribution of W. So for this one, for A, all we need to do is just remember what the normal distribution looks like. So important, it's going to be a bell curve. Okay, so it's going to be peaking at the middle, small at the edge, goes down and tapers off. So it's going to be something like this, and the mean is at this peak here. So if I just do a dotted line like so, that's where the mean is going to be, and the mean weight is 220 kilograms. And we could say here that W follows a normal distribution where the mean is 220 and the variance is the standard deviation squared. So you can say 8 squared. So it looks something like this. So all you need to do is label the mean and get the general characteristic shape correct. For B, we need to find the probability of the weight is 212 kilograms or less. So what we need to do next is remember the proportions of a curve which are included 1 standard deviation away from the mean, 2 standard deviations away, and 3 standard deviations away. So you might find this useful as a refresher. So what we're going to have here for this one where it's 212 kilograms or less is as follows. So if I just sketch on the mean, which is 220. Now think about how 212 relates to the mean. 212 is 8 away from the mean, which just so happens to be the standard deviation away. So that's 212, and this here is 1 standard deviation, that's 8. So I want to work out the probability of it being 212 or less. So the bit of a curve I'm interested in is this bit here, down on that side. By the symmetry of the curve, this bit here will be the same as this bit on the other side. So how much of a curve is within 1 standard deviation away from the mean? Well, hopefully remember what I said from before. but within one standard deviation away from the mean is 68% of all data. So what I'm colouring in yellow is 68% of the curve. This middle bit here, plus or minus one standard deviation away, that's the middle 68% of all data. So if that's 68%, in other words 0.68, then these other bits here must be 0.32 between them. 0.32 divided by 2 by the symmetry of a curve gives 0.16 in each tail. So for this one, the probability of a weight being 212 or less is this lower bit, which is 0.16. Okay, it's just this bit here, that purple bit, not this purple bit here. Although these two purple bits do have an even area, but the bit representing our probability is this bit here, 212 or less. Part 2, we use the same idea. So what's the probability of the weight of a randomly selected tiger having a weight between 204 and 236 kilograms? So again, we can use the properties of the normal distribution. So again, we know that the mean for these tigers is 220. So 204 is how far away from 220. And the same thing, how far away from 220 is 236? Well, the distance away is 16, which is 2 lots of 8. So what this is saying is these two values are 2 standard deviations either side away from the mean. 8, 8, 8 and 8. So that's 204, which is 2 standard deviations away, and this is 236, which is 2 standard deviations away on the other side. So we're wanting this proportion of the curve, which is within 2 standard deviations from the mean. And what we need to remember is that the proportion of the curve, which is plus or minus 2 standard deviations from the mean, is 95% of the data. So this bit here, like this diagram says, is 95% of the data. So the proportion, which is between 204 kilograms and 236, is 0.95. Let's have a look at another one, worked example 2. So this time, we're talking about diameters x millimeters of a bolt produced in a factory. These are normally distributed with a mean of 9 millimeters and a standard deviation of 0.3 millimeters. So again, we need to sketch and label the distribution of x. So same idea, exactly as what we did before. So I'm going to draw the curve on. Peaks in the middle, comes down symmetrically. So the mean is 9 millimeters. So we can draw this on here. That's going to have a mean of 9. Standard deviation 0.3. So we can say that x follows a normal distribution, 9 millimeters, and variance of 0.3 squared. So the curve would look something like this. So next we need to work out the probability of having a screw measured which is 9.3 or less. And again, it might help to remind ourselves of this. 9.3 or less. How does 9.3 relate to the 9 and the 0.3? Well, obviously 9 is the mean. 9.3 is here. From 9 to 9.3 is a difference of 0.3. Importantly, 0.3 is the standard deviation. So this bit here is 1 standard deviation away from the mean. So the probability of having it 9.3 or less is going to be this bit of a curve here on the right hand side of the mean, and that's 34%. Plus, of course, we've got everything on the left-hand side. So the entirety on the left, by symmetry, that's half the entire curve. This is going to be the other 0.5. So if it's 0.34, and this bit's half the curve, which is 0.5. So 0.34 plus 0.5 gives 0.84 in total. And it comes from that 0.5 plus that 0.34, this bit here. Next, for question 2, we need to work out the probability that it's between 8.4 and 9.3. So again, just to get a curve here. So 9 is obviously the mean, so I'm going to label on 9 for the mean. Then 9.3 is 1 standard deviation away, but 8.4 is 2 standard deviations away. So this time, we're wanting this 0.3 now that's 0.34 of the entire curve, 34%. And as well, we want this bit here from 8.4 up to 9. So from 8.4 to 9, that's 0.6, which is 2 standard deviations away. And we need to know that plus or minus 2 standard deviations away is 95% of all data. Now we're only 2 standard deviations away on one side of this curve. We're just looking at the left-hand side of the curve only. So this bit here is going to be half of 95%, which is going to be 47.5%. So this is going to be 0.475, which is the same as 34 plus 13.5, labelled a bit differently. So this is half of the 95%. That bit plus that bit here would be 95. Half of that is 0.475. So all we need to do now is to sum these two decimals. So 0.475 plus 0.34 that'll give us 0.815. And there we're done. Let's have a look at the next one. Number 3, given a continuous random variable x is normally distributed such that x follows a normal distribution with unknown mean mu and variance of 9, given that the probability of the observed variable being 15 or less is 84%, find the value of mu. So again, just to remind us, here's what we have. Now here, this 9 is the variance. So therefore, the standard deviation is 3. So the standard deviation is the square root of 9, which is 3. So now we can be thinking what this mu is. Okay, so I'm going to label mu here, like so. And we're told that the probability of x being 15 or less is 0.84. So that's got to be at this right-hand side of a curve, because it's more than half a curve. That point and less is 84%. So we're looking at this side of the curve. But let's just think about the significance of this 84%. Well, 84% is obviously the first half of a curve. So if I shade in the first 50%, we can now think about how much more is required. So this yellow bit is obviously just half of a curve, which is 0.5. But because it's 0.84 up to the point of 15, then I need an extra 0.34, and you can see here the significance of 0.34. It's going to be 1 standard deviation away on the other side. Yeah, so if that's 0.5, I need another extra 1 standard deviation away on the other side, which will take me to 0.34% of the entire curve. So this here is the other required 0.34. And based on this, 68% is plus or minus 1 standard deviation away. So half of that is just for 1 standard deviation away on the right hand side. And so this distance here is 1 standard deviation away. The standard deviation is 3, so that's going to be 3 away. And that will have to be the 15. So the probability being 15 or less is this bit plus that bit, which does equal 0.84. So from this we can see that mu is 3 before 15. In other words, mu must be 15 subtract 3, which is 12. And finally, question 4. We've got here that a continuous random variable y is normally distributed, but we're not told the mean or the standard deviation here. All we're told is the probability of it being 29 or greater is 0.025. The probability of it being 17 or less is 0.16. From that, we need to find mu and sigma, the mean and the standard deviation. So again, just to recap here. So what's the chance of it being greater than 29? That's 2.5%. This is 2.5%. Let's just label that. So 2.5% of the curve and 2.5% there by symmetry, that's 5%. And so what we're going to have here, apart from these tails, is 0.95%. And 0.95% is all the data within 2 standard deviations from this mean. So that must be the mean and 2 standard deviations away on either side of that. Sigma, 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 sigma. So that's 29 there. So from here, we can see that the difference between mu and 29 is 2 lots of standard deviation. So in other words, from this one, I can say that 29 minus mu, the distance from 29 here and mu there, is 2 lots of the standard deviation. Okay, so from that one, I can work out that. However, this one here, we can work out something different. So I'm going to draw a different curve for this one. That's just 0.16% chance, but it's going to be 17 or less. So what's the significance of 16% at a lower tail? Well, if it's 16% at the lower end, then by symmetry, we'd have 16% on the other side. 16 at one tail plus 16 at the other is 32%. So that leaves a middle bit of the other 1 minus 32%, which is 68%. So what we must have here in the middle is that must be 0.68 like so. Then by symmetry, the other 0.32 halved is 0.16 in each of the remaining tails. So this bit here is 0.16, and this bit over here will be 0.16 as well by symmetry. So I've just fill these in, so hopefully you can make sense of this. So 16% either side and 68% in the middle. Well, 68% of the data is plus or minus 1 standard deviation away from the mean. So this distance here and that distance there must be a standard deviation away from the mean. Whatever the mean is, of course. Therefore, 17 must be there. So 17 or less is 16% of the curve down there. So 17 must be 1 standard deviation away from the mean. So in other words, the distance in between the mean and 17 must be 1 standard deviation. So from this here, from this one, I can say therefore the distance between the mean and 17, mu minus 17, must be 1 standard deviation. We've now got a pair of simultaneous equations. You can solve this in any way you want to, really. What I'm going to suggest we do is we add both of these equations together. If we do that, over here, 29 plus minus 17, that's going to give us 12. Minus mu plus mu will cancel, and then over here 2 sigma plus sigma will be 3 sigma. So 12 equals 3 sigma, therefore sigma is 12 divided by 3, which is 4. So the standard deviation is therefore 4. We can then substitute this back in. So if we pick, for example, this bottom one, mu minus 17 equals sigma, then mu minus 17 equals 4, because we just calculated obviously that sigma is 4. Therefore, just add 17 to both sides. Therefore, mu must be 4 plus 17. In other words, mu must be 21. So that's just using the idea of proportion of areas under the curve at different standard deviations away from the mean to answer these questions. In the next subchapter, we're going to use the calculator to calculate probabilities exactly for any distance away from the mean, not just multiples of standard deviations. But for now, just as an introduction to the normal distribution, you need to try some questions on your own. So if you turn to page 40, exercise 3A, and try the whole lot, just to give yourself a grounding on how this works, that's the best thing for you to do right now. If you're stuck, do ask me. Please do subscribe and comment on the video. Give it a like, that'd be great. And if you are struggling, you know where to leave a comment. I'll get right back to you. So stay tuned, and you'll hear from me again very soon indeed, I should hope. Take care, and goodbye for now.